I would like to thank the organizers for inviting me to give this talk. So the result that I will describe today is about a result in homogeneous dynamics about equidistribution of a so-called unipotent flow in a homogeneous manifold. And there is a celebrated and famous result by Marina Ratner from the early 1990s, giving describing very precisely how the orbits of so-called unipotent flows on homogeneous manifold equidistribute, and it gives a very precise description of this. And this result by Ratner has been really had many applications within number theory and in mathematical physics. And in recent years, it has been more and more people have been more and more interested in trying to make these results effective. So somehow describe how quickly does an orbit of such a unipotent flow, how quickly does such an orbit become equidistributed in the homogeneous manifold. And what I will talk about today is a special case of such a result. So I will go directly to introduce the setting that I will consider today, and then at some point I will also give a brief, say some other results in the same area somehow. But here's the setting that I will consider. So we let G be the semidirect product of SL2R with K copies of R2. So here SL2R acts on R2 by the standard representation. Actually, it acts from the right. So we will have when we have a vector in R2, we act from the right on such a vector by a matrix in SL2R, as we see here, for instance. But now we are considering K copies of R2. So the elements in G are written as pairs, where the first entry is a matrix in SL2R, and the second entry is a vector in R to the 2 to the K. And the multiplication law in this semi-direct product we take to be as follows, that if I have two such elements in G, M1, V1, and M2, V2, the product is given by, well, the first entry is just the product of the matrices in SL2R, and the second entry is V1 acted upon by M2, and then plus V2. So this is the multiplication law. And we will consider this is a Lie group of dimension 3 plus 2K. And we consider this lattice. This is a lattice inside the Lie group. And we consider this quotient manifold. So the set of left gamma cosets in G. This is a so-called homogeneous manifold. And we also fix a Haar measure on G. And we normalize it so that the induced measure on X, the homogeneous manifold, is 1. And from now on, just to fix notation, this vector space, R to the 2 to the K, we identify it with the space of matrices, of K by 2 matrices. So then up here, V1 and V2 are matrices of size K by 2. And then this thing here, V1 times M2, is just matrix multiplication. Okay. And the results that I will talk about, they are equidistribution results in X, in this 2K plus 3-dimensional manifold. But before I start, I want to say some ways how you can think about X. What kind of space is X? So X is a torus bundle over this very famous homogeneous manifold, Y. Y we define to be SL2Z slash SL2R, and Y, well, I will speak about Y in a minute, but it's the space of, well, maybe I jump ahead. So here, Y is the space of, can be viewed as the space of 2-dimensional lattices L in R2 of such that the area of the quotient torus is 1. And the correspondence is that take any coset, here is M is in SL2R, take any coset, this is a point in Y, and this corresponds to the lattice of everything you get by taking arbitrary integer vectors and acting upon them by M. Yeah. Okay, so points in Y are just lattices in R2. And then we have a natural projection map from this X to Y that takes any point in X and just looks at the first entry M. This is a well-defined projection map, and this makes X a torus bundle over Y. The torus fiber is, well, over any, here is an arbitrary point in Y, and the torus fiber is then a 2K dimensional torus. It can be parameterized in two different ways. Most often I will use this parameterization, that you write this element of identity matrix comma xi before the M, and then xi kind of lives inside this torus. Real matrices modulo integer matrices. If you instead parameterize this fiber in this way, then V lives in a shifted version of such a torus. Okay, so that's Y. Y is a torus bundle over Y. Y is the space of lattices, and this notation will be in place throughout the lecture. Okay, so now, what should we think of about this fiber? What do we mean by? Okay, I should also say that Y can be seen as a space of lattices of area 1. It can, of course, also be seen as a space of two-dimensional tori, named, well, flat tori of area 1 and with a marked horizontal direction. And this is by identifying a point in Y instead by the quotient torus, where you mod out, you take the real plane modulo of the lattice. And then, now X, in this way, it's natural to identify the space X with the space of two-dimensional tori with K marked points inside the torus. So that's what the fiber stands for. It stands for marking K points inside the torus. And here's the correspondence that here this V is a K by 2 matrix, and every row gives a two-dimensional vector in R2 that tells the marked point inside the torus. But another way, equally natural to think about X is that X is a space of two-dimensional lattice together with K choices, or a K tuple of translates of the lattice. So a point here's a point in X, and it parameterizes a lattice in R2 together with K K choices of translates of that same lattice. Okay, so now I will state first the equidistribution result without any rate, so an ineffective equidistribution result. So on this space X, we consider these one parameter subgroups. Here's a unipotent, and I should say, when I have a matrix in SL2R, SL2R is embedded into G in the natural way that you just take 0 in the fiber. So these elements UX and AY, they are matrices in SL2R, but they are also elements in the bigger Lie group G. So UX is this unipotent flow. It's a one parameter subgroup. And AY is also a one parameter diagonal subgroup, but parameterized by a multiplicative parameter Y. And the first result that I'm going to state gives equidistribution of expanding translates of a finite U orbit. And this ineffective result stated here is one very special case of Ratner's equidistribution result. Or, well, it follows from Ratner's classification of invariant ergodic measures invariant under this unipotent flow. So fix any matrix M in SL2R, and then fix any K by 2 matrix, real K by 2 matrix. And then under a certain Diophantine or genericity assumption on psi, we have to assume that for every non-zero integer vector Q, Q is a K-dimensional vector, we have to assume that this matrix product, Q times psi, that is now a real two-dimensional vector, we have to assume that this is never an integer vector. So that's the genericity assumption that we have to impose on psi. Under that assumption, this theorem states that if I consider the following average, so here lambda is an arbitrary Borel probability measure on the real line, absolutely continuous with respect to Lebesgue measure. But when you look at this result, you may like to think about lambda as just take lambda to be the Lebesgue measure on the unit interval, or say uniform measure on any fixed interval. Then what we see here is just an average along a one-dimensional curve. This is if I want to erase. If I just look at this before I put the A there, then it's just starting at this arbitrary point given by gamma 1, 2, psi m. I start at that point, and then I flow with the unipotent flow for a finite time, assuming that lambda is a measure on a fixed interval, and I consider that's just a finite orbit of the unipotent. But then I average over this unipotent orbit, but then I take a limit where I move this unipotent orbit by the diagonal flow ay, and as I do so, it turns out that this will become more and more equidistributed. At least it becomes equidistributed on the base manifold y. And if I have assumed this genericity assumption on the position in the torus fiber, then it actually becomes equidistributed in the whole manifold X. So that this average along just a one-dimensional finite curve tends more and more to the volume average of any given test function, so a bounded continuous test function on the manifold X. And I should say that this genericity condition, that for any non-zero integer vector q, the product q times psi should not be an integer vector. That is necessary, because if it fails, then actually this whole curve is embedded inside a nice closed embedded submanifold of X. So for any given vector, integer vector q, one can easily define a certain submanifold like this. It turns out to be a nice embedded submanifold. So if this genericity assumption up here would fail, well, then we cannot have equidistribution. And I wanted to draw a picture just to give a bit more picture what we are seeing. This is a picture of the base manifold, just y equals SL to Z / SL to R. Actually, it's a picture of the hyperbolic upper half plane. But as you may know, SL. So it's this red part here is a picture of the just the modular curve SL2 Z. Take SL2Z acting on the upper half plane. So that's this red part where you identify the sites in the way you know. And now y, another way to view y is that it's a unit tangent bundle of this hyperbolic surface. So when I see this red two-dimensional surface, for me, you can, if you think about the unit tangent bundle, it's a three-dimensional manifold, and that is y. That is another interpretation of y. And the orbit that we are integrating over, supposing that lambda is just a uniform measure on an interval, and then just looking at the base manifold, then the orbit, supposing that M, this fixed matrix, is the identity matrix, well, then the point I'm seeing here is just X plus IY in the hyperbolic plane. So then what I'm integrating over is a piece of, as you know, this is a closed torocycle if I just integrate along a horizontal line. So I'm integrating along X goes through some fixed interval, and then I let Y tend to 0. And it's a well-known fact that if you integrate over a fixed interval, you let X go through a fixed interval, and then you let Y go to 0, then this part of a closed torocycle becomes more and more equidistributed on the modular curve. And actually it becomes more and more equidistributed in the three-dimensional manifold Y. So that's a well-known result. But the result I'm stating here is that this holds even if you look at the fiber also. You become equidistributed in the space X, assuming that you impose this genericity assumption. So that's the ineffective equidistribution result that now I want to speak about how to make it effective, to make an effective version of this, telling how quickly this equidistribution takes place. But before I do that, I just want to mention that, as I said, Ratner's result in general has found many applications both in number theory and mathematical physics. But also this particular case that I'm discussing here, where for my particular group G, that result that I have just stated has found many applications in, well, this is a more or less number theoretical result, and here's a rather famous application that if you do it just for k equals 1, when k is equal to 1, this group G, remember G is the semidirect product of SL2R and R2 in this case. And when k is 1, then this is known as the affine special linear group, and it acts on R2 by affine linear maps. So in that case, Elkis and McMullen used this to get an understanding of the limiting gap statistics of the sequence square root of n considered modulo 1. But also here are some applications in mathematical physics. So all of these applications of this equidistribution result have been known for quite some time, but it's a kind of, here in this result, if you don't have any statement about the rate, so you don't know how long you need to wait in this limit until you are fairly close to the limit, and that then carries over to all these results. So it seems to be a kind of an interesting task to make this effective, to tell how quickly do we approach the limit. But now I want to explain the effective result that we prove. Oh, I should have said from start, it was on the first slide, but I should really have mentioned that all of what I'm going to talk about today is joint work with Anders Södergren and Pankaj Vishe. And we are still finalizing this, but we hope to post a preprint fairly soon about this. So here is a statement of an effective version of the previous result. And here I just fix some numbers that have to do with what Sobolev norms I consider. I don't think I will go into those details, but I want to make clear that we have precise Sobolev norms. We are rather precise about what norms we use. Then the result is like this. So fix any test function on the manifold X. And now we need to assume that this test function is differentiable, n times differentiable, and that it has a certain decay. Alpha captures a decay in the cusp. Previously, I mean, the ineffective result we could say for arbitrary bounded continuous functions, but it's well known that if you want to have a rate, you usually need to restrict the test function to be somewhat smooth. And also the measure, previously we were integrating with respect to an arbitrary absolutely continuous Lebesgue measure, absolutely continuous Borel measure on the real line. But here again, we need to take it to be somewhat smooth. So now I have to take this measure to have a density that is at least 5 times differentiable in this result. So we restrict to more smooth test functions and test measures, so to say. But for such f and h, then for arbitrary m in SL2R and an arbitrary k/2 matrix xi, we have that this ergodic average that I just described before tends to the volume average of f. And here I didn't assume that h is a probability density. So here I have to take the Lebesgue average of h also. By the way, this number 43 says that we require h to decay quite rapidly. Basically, you can take required h to have compact support, if you like. And the statement is that this difference of the one-dimensional average and the volume average decays. Well, it's bounded by this from above. And here we have just some Sobolev norm of f, Sobolev norm of h, and then this is a Frobenius norm of the matrix M. Basically, since we have this big power 13, we basically need to take this M inside a compact set. Otherwise, this blows up quite a bit. But the really interesting object in this product is this delta psi sub y. I'd like to call delta psi y some Diophantine majorant function. And the definition of delta psi y is here. So delta psi y is you add over all integer vectors q, non-zero integer vectors q, and then we also have to have the sum over all positive integers d. And then it's just the sum of positive numbers. So it's really a majorant sum. Well, we add over, but to get familiar with this sum, let me note that even if we would assume that this whole thing here is just 1, the thing I just encircled is less than or equal to 1. Even if I assume that this is 1, then I have an absolutely convergent sum here because m is assumed to be larger than k. And sigma d is just the divisor function. So it's an absolutely convergent sum. This is some kind of weight. But the point is that this number here is less than or equal to 1. And supposing that psi is favorable, so supposing that psi satisfies the genericity assumption that I stated before, that saying that q times psi is never an integer vector, then actually, so let me explain notation. D times q times psi is a real two-dimensional vector. So it's a point in R2. And this norm, I shouldn't call it norm, this norm with a z here, that stands for the distance of this point in R2 to the point, to the nearest integer point. So it's immediate to see now that if we assume that for all integer vectors q, non-zero integer vectors q, that this vector is not an integer vector, well, then this also holds if I put a d in front, because just replace q by d times q. And that means that the number here in the numerator is positive, it's not 0. And then because of the absolute convergence I just told you, we see since when y goes to 0, this number here inside the blows up to tends to infinity, and then I take it to the -1. So we see that each individual term in the sum will tend to 0, and because of the absolute convergence I told you about, we see that the whole sum tends to 0. So the result stated here implies the previous result, at least for these smooth type of test functions. But then it actually, you can a posteriori do an approximation argument. So this result stated here implies the previous result in full. But the point is that we now have a rate. Here we say that when y tends to 0, this is an explicit expression telling how quickly the one-dimensional average tends to the volume average. And I want to explain a bit more about this result, and especially what rate do we actually see here. But before that, maybe now is the time to give some background, just state some other results in this area. As I said, it has been a really hot areas recently to seek for effective equidistribution results and effective versions of Ratner's result about unipotent ergodic averages. And there is a big literature on this now. Here I'm just stating a few. Well, first of all, I wanted to state these are really breakthrough results, quite recent. And Elon Lindenstrauss has given a talk about this a few years ago. So here's a result by Lindenstrauss, Mohammadi, and Wang. They work instead on quotients of this Lie group, SL2R times SL2R, or G equals SL2C, and consider one-dimensional unipotent orbits again, and manage to prove an effective version of Ratner in this setting, if the lattice gamma is an arithmetic lattice. And this is somehow really breakthrough results. It's much more difficult than what I'm going to talk about today. It uses, it's a deep study of random walks to get this, and they use projection theorems from fractal geometry, and a notion called discretized dimension, and many other tools which are developed in this quite long and complicated paper. And similar, building on similar methods in part, also there are some results giving effective equidistribution of special unipotent orbits in this space of three-dimensional lattices. yeah. So what I'm going to talk about today is much easier. I use what we use in our work is tools, harmonic analysis, Fourier decomposition, and tools from analytic number theory. But one difference is also that we get quite a good power rate. As you will see soon, if psi satisfies some Diophantine condition, then we have a good power rate in this delta psi sub y actually behaves like a quite nice power of y that we can specify. Whereas here, they also get power rate decay under Diophantine conditions, but this power is really tiny, and maybe not easy to even specify.
Sorry, Andreas. Elon is asking why special? I think general.
Where did I say special?
Elon, please also unmute and...
Just a small comment. I mean, it was what Andreas is doing is very impressive, and I don't agree with that statement of his. But as far as I understand, any unipotent one parameter orbit in SL3R modulo SL3Z is covered by our results.
Oh, that I had not understood actually. So this cover. Thank you for pointing that. So you actually handle an arbitrary special. Wow. Okay.
So there are two kinds of unipotent groups. One of them Lake did by himself, and the other kind we do together. In SL3R modulo SL3Z, there are two kinds of unipotent orbits. So.
Okay. Oh, thank you. So that was really needed to be corrected. Thank you. Okay. So that's quite impressive. Okay, and here I just list some previous work in the same kind of area. So I had an earlier paper where I did it just for k equals 1. Remember, when k is 1, then G, my Lie group G, is the affine special linear group. And then Tim Brown and Ilya Vinogradov, building on the same techniques, they handled a different type of unipotent orbit. And this had application to this Elkis-McMullen description of the local statistics of square root of n mod 1. And then together with Pankaj, I have also worked on this case, the same setting that we have today, but with the different, that we weren't able to handle arbitrary unipotent orbits for this given unipotent subgroup that I'm discussing, only rather special orbits, but still it was enough to have some applications to quadratic forms, questions about local statistics of inhomogeneous quadratic forms. And then there's also a work building on quite different methods again. So more towards these methods, maybe thinking about the random walk and by automorphism on the torus fiber. So by Woo-Yoon Kim, he has obtained effective results for. So here you consider, here is the space of d-dimensional affine lattices or d-dimensional grids. And here Woo-Yoon proves equidistribution for expanding translates of so it's unipotent d-1 dimensional orbits which project on the base manifold on SLDR. They are the full Horus spherical. Yeah.
Sorry, Andreas, to interrupt you again. Christopher has a question. Christopher, would you please ask me?
Yes, thank you. I've got a question about so in the statement of the theorem, you've got this function delta.
Yep.
And so I see that you've got these assumptions on the weights. I'm surprised that the function delta decorrelates the dependence on psi and on m. I would have expected that psi and m, you would get a weight which would depend on both, but it seems like you are able to decorrelate them because you've got enough assumptions so that you only need to care about the norm of m and the point psi. But I would expect something like that the Diophantine approximation properties of the vector psi in the lattice also depends on how it is with respect to, how it's m orbits.
Yeah, it should be pointed out that when I write, so somehow this combination here is a way to write the general element in G. But when I write it like this, then psi is really taking modulo the integer matrices. So it's kind of natural. This site
I
tells
see.
where you are in the torus. Even if the torus is shifted, it tells somehow. Yeah, as I tried. I hope it makes sense. So it's, and then yeah.
Okay, thanks.
Yeah. So some more comments about this. Just the result. Okay, I'm not going to tell about what notation for Sobolev norms we have, but some more just comments about the decay. I already said that we get a power rate. Actually, this delta psi sub y generically, if psi is generic, then it's a generic with respect to Lebesgue measure, then it decays like essentially y to the 1/4. And this is, but it never decays more rapidly than that. It's trivial to look at this sum and see that it is always larger than y to the 1/4. And then you can also work out if you have some type of Diophantine condition on psi. And here we have just done some naive observations that if you assume that either the first column or the second column of psi is what we call kappa comma alpha Diophantine, well, then you can deduce some power rate decay depending on what kappa and alpha is. And kappa comma alpha Diophantine, well, kappa Diophantine for me now here means just the kind of linear form Diophantine condition that. So here V is either the first or the second column of this matrix psi, and now consider any so Q. You can think of Q as a linear form on RK, and we ask how far is Q applied to V? How far is that from an integer? So here this is a real number, and how far is it from an integer? And assume that this is bounded from below like this. This is a very standard Diophantine type assumption on the vector V. We needed to impose something slightly different, that you wait, if you multiply this Q by here when you see this condition, it's always you need only impose this for primitive vectors Q. But here we wanted to put the condition that gives somewhat more assumptions if you take Q to be some multiple of a primitive vector. So that's what we mean by kappa comma alpha Diophantine. But we can see that, understand at least some facts about this notion. For instance, that it holds for what should I say? Yeah, you can get bounds on the Hausdorff dimension of the complement set. So in particular, for any kappa greater than k and any alpha greater than 1, this Lebesgue almost all vectors V are certainly kappa comma alpha Diophantine. And as a consequence, one gets if using some rather difficult results by Wolfgang Schmidt, you get that supposing that either the first or the second column of psi consists of real algebraic numbers, and assume that one and the entries of this column are linearly independent over the rational field, well, then you will get some power rate decay with an explicit power. So that's kind of a point that to make here, that the Ratner gives you equidistribution for really specific conditions, and not just a rate. We don't have here a rate just for Lebesgue almost all, but we can tell a rate for specific real algebraic numbers or matrices here. What else? I had some more. So now I wanted to turn to a second main result, which we obtain as a corollary. And the way to get this is kind of well known, but still it was satisfactory for us that we could apply this first result, which was about expanding translates of a fixed piece, a fixed unipotent orbit, a fixed finite unipotent orbit. We could, it is strong enough somehow to apply to give us effective equidistribution of long pieces of unipotent orbits. So what we consider here is an ergodic average where we fix a point gamma g in X. And then we consider a longer and longer ergodic average. So here we have to consider kind of smooth ergodic average, but to first digest the statement, you should pretend that H is a characteristic function of the unit interval, say. If H is the characteristic function of the unit interval, then this is just the standard ergodic average from 0 to capital T. So we take length, we follow this, we start at the point gamma G and follow the unipotent orbit for time capital T, and we average the test function F along that finite curve. And then we this effectivizes the result, saying that when capital T tends to infinity, this one-dimensional average tends to the volume average. Now, we cannot directly get the statement for such sharp cutoff ergodic average. We could get this a posteriori. It's easy to approximate this. We have to assume that we take a smooth cutoff in the ergodic average. Then we get the cleanest results. But if you are willing to sacrifice, here, I assume in the statement that the support of H is contained in the between -1 and 1, so I can just as well take C5 norms. So this is a norm involving, it's the supremum norm on H and its first 5 derivatives. So what I was saying is that afterwards, after the fact, somehow you could do if you want to get results for sharp ergodic averages, you could do an a posteriori approximation argument, but then you would get the kind of tiny power of what we see here. I don't know. I haven't thought about how tiny, maybe 1/10 or something. So it's cleaner to state it for these smooth ergodic averages. So here we fix a point gamma G, and the result states under favorable conditions, it turns out that this long complicated expression that I will soon explain, this long complicated expression tends to 0 when capital T tends to infinity. So it gives us that this smooth ergodic average tends to the volume average. And here I wanted to explain the notation. Again, it's kind of nice. This exactly captures the conditions that you get if you work out what Ratner's ergodic classification of ergodic measures. You cannot have, this cannot go to 0 for arbitrary starting points gamma G. There is no chance it could, because if G is not suitably generic, then all of this orbit will be confined inside some homogeneous submanifold. Okay, so I want to explain the notation a bit. So I have to explain this YGT and then this BGQ, T that appears inside here. But the point will be that, let me turn to the notation. So YGT, that looks at the, remember G is an element in G, and soon I will actually write, as I did before, the torus fiber part is given by Xi, and then M is the matrix in SL2R. This YGT looks only at the M. So it only cares about the projection of gamma G to the space Y of lattices. And what we look at is, this is a very basic picture when you study the horocycles in SL2R, or for instance. So we look at the point gamma G, but project it down to Y. And then we flow by this diagonal flow AT. That means that we follow the geodesic flow for a time log T. So here's the point gamma G. The point is that we following the geodesic flow, this is the contracting direction for the horocycle. So from start, I have a horocycle of length capital T, but this flow will move that horocycle and make it to a horocycle of length 1. And it's well known somehow that the properties of this horocycle inside the space Y depend on where the position of this point, gamma G AT. Anyway, here, and now we take the cuspidal height of that point. This is just, if you take the pullback of that point into the standard fundamental domain in the upper half plane model, and then take the Euclidean imaginary part, the Euclidean height of that point. That's my cuspidal height here. And we have to assume that this divided by t tends to 0. So that then and only then will the first term in my bound tend to 0. And it turns out that this happens if and only if the projected curve in y is not a closed horocycle. And then it's a well-known fact that every non-closed horocycle in y actually equidistributes in y. So, so at least we have a chance to become equidistributed. Yeah, so that's the explanation of the first term here. But the second term is, of course, kind of more interesting. This tells when I also become equidistributed in the torus fiber variable. So here I wanted to explain this notation. So BGT, what we need in order for the sum to converge to 0 is that for every g, well, g is fixed, but for every non-zero integer vector q, I need that BGT tends to plus infinity when t tends to infinity. And BGT is defined as follows. For any given integer vector q or non-zero integer vector q, it's the supremum of all L such that L times this rectangle RT, and RT is a rectangle that is very tiny in the horizontal direction, but it has size, goes from -1 to 1 in the vertical direction. So you could see this picture here. This red rectangle is might be this RT. And then we want to dilate or scale up this rectangle as much as we can, but we ask what's the largest possible scaling of this rectangle such that it avoids all points in this affine lattice or this grid here. And what is this grid? Well, this grid is determined by some projection of G. So I have to tell you what this projection map A sub Q of G is. Well, A sub Q is a projection from G going to ASL to R. Remember, ASL to R is just SL to R semidirect product R2. And what the map does is just it takes an arbitrary element in G, and here V is a k/2 matrix. And now just take Q times V. This gives me a vector in R2. So that's my projection. And this map, if Q is an integer vector, this map descends to projection from X, my 3 + 2k dimensional manifold, to this 5-dimensional manifold, this space of affine lattices. And this projection map is kind of very natural. If you think about X in the way, remember X is the space of flat 2-dimensional tori with a marked horizontal direction together with a k tuple of points. Then if you have a k tuple of points in the torus, you can form any interlinear combinations of those points. For instance, 3 plus the first point minus 5 times the second point. That's again a well-defined point in the torus. And what this map does is just Q tells us which interlinear combinations to take. So what we do is we have a k tuple of points in the torus fiber, and we take Q1 times the first point plus Q2 times the second point, and so on. And that gives me one unique, well-defined point in the torus. So that's this projection here. And now so BG, Q, T tells how big scaling of this long and thin rectangle can I have to and still avoid all points in this grid. And now it's rather immediate to see that for a fixed non-zero integer vector Q, this BGQT tends to infinity, if and only if this affine lattice has no point along the y-axis or the vertical axis. That's more or less immediate to see. But the point is that somehow this condition, if it fails on the other hand, if this affine lattice for some non-zero integer vector Q has a point on the vertical axis, then that's an obvious condition that means that my unipotent orbit cannot be equidistributed. Because, I should say, in this picture, the unipotent flow acts by shearing. So the points the unipotent flow acts by shearing. So all points on the vertical axis are fixed. Points to the left of the vertical axis are moved downwards. They move further downwards, the further away to the left they are, and they move upwards, vertically upwards, if they are to the right of the x-axis. So my point is that if this condition, if this affine lattice has a point on the vertical axis, then that point remains fixed as I flow by the unipotent flow, and it means that my unipotent orbit is contained inside the homogeneous, non-trivial homogeneous submanifold of X. So there is no chance of becoming equidistributed. Yeah, and I just point out that this bound here satisfies a kind of satisfactory decay rate, at least for generic initial conditions. One can verify that it decays like t to the -1/4. And similarly, this YGT can be very explicitly connected to the Diophantine properties of this matrix M, the SL2R matrix M. And in particular, one can see that YGT tends to 0 as t to the -1 plus epsilon. So it means that for a generic M. So it means that generically, this whole expression tends to 0 as t to the -1/4 plus epsilon. So now I have only a few minutes left, and maybe I just give some impressionistic things about the proof. I guess the proof of this, the fact that theorem 1 implies theorem 2, I think it's well known to the experts how to do it. Somehow what was satisfactory to us was to see that, it's harder if this is the point that I said is directly related to how the Horrell cycle equidistributes in H. And if this point has large Caspital height, then you have to do some kind of partition argument of, well, I haven't told you of what it is, but then you have to apply theorem 1 several times to get our result. If this point has kind of bounded Caspital height, then then the result is immediate corollary of theorem 1, actually. So what was satisfactory to see that if you apply our theorem 1 many times, as you have to do to treat this case, and you collect the error bounds, then you can handle this sum of error bounds, and you have to do a little analysis of this. Somehow think about the definitions, plug and evaluate, find a way to handle these infinite sums and bound all these positive terms, but and then interpret it in the way of as I have interpreted it up here. But yeah, and I think I have a few minutes. Please interrupt me if that's not the case. But so maybe I can give again some impressionistic words about the proof of theorem 1. So yeah. And here is a recollection of what theorem 1 says, but I don't have time to recall that. But the basic method is, as I said, Fourier analysis. So what we start by is we have f is a test function on X, but we view it as a function on G that is left gamma invariant. And then we do a torus expansion of this function in the torus variable. So then, but even this, I think I will go directly to just say what the sum that we, after having done this torus expansion, the kind of sum that we have to prove non-trivial cancellation in, it actually looks like this. It's a sum over all matrices in SL2Z, and then here is a linear combination of A, B, and C, and D with some, hopefully, numbers that are not all rational. Like if all of these numbers are rational, then we fail. Then we will not have cancellation in general. And then FM, whatever, it's a function on SL2R. We can think of it as some smooth function with some decay on SL2R. And inside there, we plug in ABCD. ABCD goes through SL2Z, and then we do some kind of Horrell cycle average. And well, here's the cancellation result that lies at the bottom of this. It's a result that we prove. So it's a cancellation result in exponential sums, where and this is for an arbitrary test function on R4, having some rapid decay. When you look at this, you should think of F as having compact support, say, and at least 5 derivatives we need. Well, okay, when you look at it from start, you might think of F as being a smooth characteristic function of a unit ball in R4. And then this is just an exponential sum over all integer solutions A, B, C, D to this. We have relation, and then we have a linear form. And we prove a cancellation in this type of exponential sum. The trivial bound, so we are adding essentially up to A and B and C and D are less than X. And the trivial bound would be of order of magnitude X to the 3. But it turns out that this is a similar type of Diophantine majorant, as I have discussed before. It turns out that this is a good majorant, so long as this vector alpha is not a rational vector, essentially. And I think my time is up there, so thank you.